Now for homework of section 5.6, please do on page 522 problems 319, 21, 25, 27, 31, 35, 37, 41, 43, 49, 51, 53, 55, 57, 59, 65. Now that sounds like a lot of homework, and it is, but well, not all of them are long and tedious. In fact, I think most of them are fairly short and straightforward, though there are a couple long and tedious ones. And so that it's important to do a bit more homework than average, because is important to be good at handling infinite series and figuring out if it converge or diverge, because that's going to be used in the next section. I mean, next chapter. So so please go do your homework, and when you come back, then I will want to talk about it. All right, now that you're done with your homework, wow, so fast, right? And let's talk about the homework. First, problem 327. We have a situation where you have the factorial. As the book mentioned, when you have the factorial, usually the ratio test works nicely, where you take the ratio and then see what happens, right? And the benefit of the ratio test, as always, is that you don't have to come up with some other series to compare it with. You just compare it with itself, and then see if anything good should come out of it. So let's take a look. So I did exactly what I was told, right? Here is the self-comparison right there. And once you did the comparison, and you see that I'm stuck with quite a bit of algebra that involves the factorial. Make sure you know how to do the factorial algebra, okay? If you can't remember, if you can't figure out how this is done, then better go look up some factorial exercise and do them until you're refreshed as to how factorial works. But anyway, so if you get through this mess and not mess up, see, I didn't mess up the first time. How cool is that? And then so eventually you get down to something like that. And so now what? So then now you look at the inside of this thing. This thing is being squared, I guess. And so look at the inside. What is that thing? So we'll only work on the limit of the inside. So I let y equal to n over n plus 1 over n. And then I recognize that over here on this side, 1 over y is this thing, okay, which can be rewritten as that. Now, what is that? Now, if you might remember that we have done this thing by now, I don't know, 7 times or something since Calculus 1. This goes to e. Or you can take the natural log of this thing and apply L'Hopital's rule and all that stuff, which we have done 7 times. Okay, so this time I'm not even going to bother doing it. I'm just going to tell you that this approaches e. Okay, this value right here. So therefore, y itself then approach 1 over e, and then the row approach 1 over e squared, which is less than 1, being that e is over 2. Right? So the squared is definitely less than 1, and therefore the series converges by the ratio test. Yeah, so I think that's all I want to say about that. So let's go to the next problem, which is problem 327. Now that one's more involved because you got stuck behind a big pile of algebra, but otherwise it's fairly straightforward. Right? And the next problem is even more so. What are we doing? I think the root test. Okay, the next problem looks kind of complicated. You have natural log, and then you have natural log within the natural log, etc. However, if you apply the root problem, things look pretty neat, right? First, you come up with some natural log, and then I guess I took it's an infinity over infinity situation. So I took the L'Hopital's rule and took the derivative, top and bottom, and end up, when n goes to infinity, it converges. See, because it goes to 0. And by the root test, if it goes to 0, as long as the row is less, was it row? Whatever. The point is, if it goes to 0, it converges. As you can see, my explanations, and somewhat lacking. I should write it out better. So please write it out better if you can, okay? Don't learn to be lazy like me. Theoretically, you should write it out better, and most calculus teachers would require you to write down the proof neatly and cleanly. I will, for these kind of problems, I usually can't get myself to do a better job than this. But when the problem becomes more complicated, I do write it out better, because if I don't know what I'm talking about. Okay, so that's how it is. But in your case, but for you, please write it out as clean as you can make yourself to do. That would be, and so that everything is neat and perfect. That's mathematics. Okay, so next let's look at problem 341, where an is equal to that thing. Okay, again we use the root test, and this one is even shorter. Okay, you take the root, and again it equals to that thing, except with a minus sign. A minus sign is it end up being 1 over e, because it end up being, yeah, that's, again, we've done that many times. And if you can't remember how that's done, use the take the natural log of the expression, then use the L'Hopital's rule. Yeah, like the couple problems we did earlier, the same thing. Anyway, is 1 over e is less than 1, therefore the series converges by the root test. Next, let's look at problem 343, and you have this one looks harder, well, somewhat more complicated, but luckily there's a hint that the book provides in this previous problem. See, it says see hint for the previous problem, 342. And so what we're gonna do is we're gonna draw out the area under the curve. Okay, first I did, you see the part I scratched out, I did the less than situation. And then I realized that that's not what we care about. Okay, because less than does zip. So then I tried again, scratch that out, and then do the more than. And then the only difference is you have to draw the area under the curve, the rectangle, whether it's above the curve, stick out, or is under. And then if it stick out, then it's bigger than the integral. All right, and then you make sure that everything works out. So in this case, the rectangle goes from k plus 1 to k, drawing it this way. That's the k plus 1 rectangle, and all the way to k is together is going to be bigger than the area under the curve of 1 over x. And then when you round up the math, then this thing end up being bigger than 1, and therefore by the root test it diverges. All right. Next, let's look at problem 345, which is a generic problem, which is the ratio test. Okay, it looks like a ratio test might work out. So that's what I did. So I did the ratio. Look up here, see? I wrote things down, and then I did something that screwed up. Okay, in any case, I calculated something, the whole thing to go to infinity. So I said it diverges. And then I look at the answer, and it said the answer says the opposite. It converges. So I scratched that out. Okay, try it again. Redid the algebra, and this time I got it right, or something. Anyway, so I got through the end of the algebra, and yeah, eventually figured out it goes to 0, not infinity. Big diff, right? I mean, that really matters. So anyway, I show that it goes to 0 because it is less than the geometric series, because the inside here, as n goes to infinity, it's going to be less than 1. So if you by the comparison test, if you compare it to any geometric series that converges, this thing has to converge. So that is 345. Next, let's look at problem 347, where we have an is 1 over xn. It has odd definition. That's different than normal, where xn is defined recursively as xn plus 1 is half xn, etc. And that's, which is okay. And then of course x1 equal to 1, which is fine. Okay, and then how are we going to do this? We are going to, oh, sorry, there is a nth power here, otherwise who cares about this thing? Anyway, so there's an nth power. So how are we going to show that this series converges or diverges? Well, we're going to use the root test, being that there's an nth power, right? So we apply the root test, and then the root test shows that the nth root, of course, is conveniently 1 over x to the power n. I mean, just 1 over xn. Not power n, just xn. The question is, well, where does this go? Does it converge, diverge, anything? And where did but 1 over xn is this mess here that we have to deal with. And so the first thing I did is just see what it looks like. So I wrote down a few things. X1 is that, and do some basic math, applying it into the recursive formula. So I came up with a bunch of numbers. The second one, x2 is 3/2, and then it becomes 17, 12, and x4 is 1.414, which is 1.414 is a very specific decimal that, if you might remember, it equals to square root of 2. But so I did 4 numbers. Does that mean this whole thing goes to square root of 2? We don't know. Okay, but however, there's a chance that, and being that we are considering 1 over xn, for this thing to converge, the root test says that you have to be less than 1, right? So if xn is bigger than 1, then this will work. Now remember, the root test has to approach something that's bigger than 1. Therefore, we need xn to approach something that's bigger than 1. Okay, so it looks like xn is gonna be about 1.4. So maybe. So then so I decided to choose it to be bigger than 1.1. See what happens. See, so I thought, is it more than 1.1? So to investigate that situation, here's what I did. What I did is, so we have this formula, and then let's consider this part. And to avoid, there's an n there, I think. Yeah, my n is written on the wrong place. Okay, it's not the power, it's just 1 over xn. So to investigate this situation, and is this thing, x1 is 1. For anything bigger than 1, is this thing going to be more than 1.1? Because we need this thing to be more, each one, if it was each one more than 1.1, okay, then so if x, my question is, let's write down the question, is xn bigger than 1.1? Okay, question mark. If it is, then 1 over xn will always be less than 1.1, which means that this thing will approach something row that's strictly less than 1, which means it's going to converge. So by the root test. So I need it to be bigger than something slightly bigger than 1, okay? But it has to be bigger than 1. Remember, if it approaches 1, then the root test has no information. In other words, you did it all for nothing. So you have to find a number strictly bigger than 1, but it doesn't have to be a lot more, okay? Slightly more is enough. So I picked the number 1.1 to check it out, to see if it works. So to do that, what I did is, let's say I picked some variable. Let's c equal to x of xn, because I don't want to write xn all the time, plus it gets confusing. Well, okay, so then we have this situation, right? 1 over 1/2 c plus 1 over c. The question is, let's subtract this thing minus 1.1 and see what it does. Yeah, that is this thing bigger than 0? Sometimes, anytime. And for what value of c is this thing bigger than 0? So I'll write down a question mark here, okay? C, and then okay, so there's the question. Now, having done that, then we rework this equation by multiplying c across the board and stuff. So then what you get is eventually you get, let's see, c squared plus minus 2.2c, and plus 2 is bigger than 0. Again, that is the question. Is this thing bigger than 0 for certain values of c? Now, and then I plotted this thing on the graph that looks like this on the graphics calculator, and turns out this is true for all c, okay? In other words, this relationship is bigger than 0 no matter what value c is. In other words, the xn, what we had before, this thing right here, which is where this come from, right? This thing right here, we can write down that 1/2 xn plus 1 over xn is always bigger than 1.1. that is for all any and all value of xn. Doesn't matter what it is, it just happens that way. Okay, and so once we know that, but this is equal. What is this? This is equal to xn plus 1, right? And therefore we know that the root in the root test, the root test of an, which is 1 over xn, is always going to be bigger than 1.1. Yeah, for n bigger than 1, because x1 isn't bigger, but everything else is. Okay, and that's all that matters to us. And being that, therefore, by the root test, it converges. See, that is the end of the solution. So this is a kind of an interesting problem where it has a slight twist that you can work on, but twist happens to be very convenient. See, it just happens to end up being a quadratic equation that is always positive. No, it has no real roots, which is great. So it conveniently helped us. Okay, so that is that. That's the end of 347. Sorry, I wrote this thing wrong. It should be 1 over 1.1, right? Because xn was bigger than 1.1. Yeah. Anyway, so then it's more than 1 over 1.1, which means it's less than 1, and therefore it converges. Next, let's look at problem 351. You have a bunch of stuff raised to the power n. So the first thing we do is apply the root test or something. Did I apply the root test? I guess not. Or why didn't I apply the root test? I don't know. Doesn't matter. The point, I guess here you just apply any test you want. So then what I did is, I just did the same old thing we always do. Is I took let the function, okay, I changed it into the function form, applied the natural log, and then used the L'Hopital's rule to, I think the root test might not work because they're too close. So if you do the root, the limit will go to 1. That might be why I didn't apply the root test. Either way, the point is we get to the L'Hopital's rule, and where you have to work on fractions, okay? But it comes out pretty nicely as long as you don't get the fractions messed up. Please rework fractions if you have trouble in this area, okay? You should know how to do fractions, no matter how complicated it looks, if the principle is the same. So anyway, so you get through all the fractions, and eventually get to some point where the natural log of y approaches -2, which means, it gets over here too. Anyway, so then y approaches e to the power -2, which is less than 1, right? There is, what? Give me a second. What? Oh yeah, right. Never mind. Now the point is this thing approaches e to the power -2, which means an itself approaches a solid number. It doesn't even approach 0. And by the divergence test, if each term doesn't even approach to 0, then it automatically diverge. Okay, each term only applies to e to the power approaches e to the power -2, and this doesn't even satisfy the requirement for convergence. That actually makes sense if you look at it, because the top term and the bottom term isn't that different as n approach infinity. You know, imagine n to be a trillion. What's the diff between the two? Maybe not much. However, that is not a sufficient argument necessarily, being that stuff is being raised to the power n. Who knows what that does? So it's better that if we do the calculation and prove it exactly, that it does approach a specific number, and therefore it diverges. And that's 351. And then next, 357, we have a situation where 357, where we're doing something that's a lot of algebra again. And then remember what this means. This means something, well, the book tells you what it means if you remember this from probability. That is, probability is taught in algebra, I guess. Yeah, everything's taught in algebra, but or maybe a little bit later, like pre-calculus. The point is, that's just a notation that means this, okay? It's called the combination, the NCR. But anyway, you have this thing, it means that. And then which means you got stuck with a whole bunch of algebra that's involving the factorial. So then you plow through the factorial, which factorial problems usually cancel out very nicely, as you can see. This problem is stuff canceled out neatly, but still you end up with a pile of stuff, which what you're gonna do is divide by k. Okay, k cubed, top and bottom. That's each k gets divided out. So you end up with this thing, which end up with that, which end up being less than 1. And therefore it converges by the ratio test. I guess that's what I was doing. So from the very beginning, we're doing AK plus, right here, AK plus 1 over AK, because you have a lot of factorials, and factorial problems usually works well with the ratio test. So you apply it, and there it is. It converges by the ratio test. So that come out pretty nicely. Now, by now, when I was doing preparing the homework, I feel like I'm getting sick of doing this stuff. Okay, it's like, it's like too much of a good thing. Now, if that's how you feel too, and you might think maybe this is a sign that I shouldn't be doing any more calculus. This is my limit. No, it's not. Okay, this is we're at the very end of the section of the chapter, and after this, we're gonna do something else, which is related to series. But it'll be something else. Series is just becomes a small part of it. So so this does not mean you should quit. Please don't quit. It's not time yet. Anyway, we'll just tough it out. If you're kind of sick of it, please take a break. Maybe do the rest of it tomorrow or something like that, and until you feel refreshed and ready to tackle it again. And instead of quitting, please do not quit. Okay? I mean, at least this doesn't prove that you should quit if you're just sick of doing series. There's a lot other more interesting stuff coming in calculus, and series is by no means the end of the story. Okay, things get better. And so anyway, the next problem we need to do is 359, which says AK equals to all the stuff. Okay, that's good. So it's raised to the power 2k. So the first thing we do is, of course, the first thing I did is, of course, apply the root test. So I applied the root test and calculated what it might become, and turns out it becomes this thing is going to be less than 1, equal to 1. As it goes to infinity, it approaches 1. Okay, in other words, as you remember, the root test, if the row approaches 1, you know nothing. You did it for nothing. All right, and so but we do know that this whole thing is going to be less than or equal to 1. The reason is because the denominator, okay, is always somewhat bigger than the numerator. Therefore, it can never go past 1. But the problem is, if it approaches 1, we can't prove that it's going to approach anything less than 1, right? So if it approaches 1, then we can't apply the root test. And so the second trick, we're going to use what the book says. The book provides a hint, I think in a previous problem maybe. And yeah, so we're going to use what the book says and manipulate the exponent. Okay, we are going to do that. And then we're even gonna do this. Okay, minus 2k is minus 2k multiplied by the frac natural log k over natural log of k, and then we make it look even more complicated to look like this. Why? Because this is the hint that the book says. So we'll follow the hint and hope that it leads us to something good. And then so keep going. We have following the hint, I rewrite the whole thing out. So the expression now looks a lot more complicated than it used to be. But after you're rewriting, you notice the stuff inside the bracket approaches e. That's because e, as k goes to infinity, that's the same as this expression right here. So it's identical. If you let n equal to natural log k over k. So as that goes, they're both going to infinity. So as it goes to infinity, you know that expression goes to e. So the entire thing inside the bracket just goes to e. So so that is which is a fixed number. So we can just substitute that as e to the negative natural log k squared, which happens to be 1 over k squared. Okay, and that is p series with p equal to 2, and which converges. And so after all that, so yeah, so then it converges. Right, which seems like a bit of a stretch, but we will accept that proof as we'll accept it, right? And then that's the end of 359. And finally, we are going to do 365. I think, okay, so for 365, I did the ratio test, okay? Because so we do the ratio test, and so we have, what do we have? We have this thing equals to, and the ratio test shows that as long as x is less than 1, then the whole strictly less than 1, okay? Because the k squared over k plus 1 will approach 1, all right, if you do the math, or just remember how that works. Applying the limit, as long as x is strictly less than 1, then this limit will go to something that's less than 1, and for the ratio test, it will converge. Now, the answer in the back of the book says that x can be less than or equal to 1. That is not true by the ratio test. However, we can prove that to be true in some other way. That is, what if you then further examine what happens when x equals to 1? If x equals to 1, then now let me see. Now for x equal to 1, then the ratio test doesn't work. So we'll plug x equal to 1 into the original an. Okay, then the whole thing on top, the entire denominator becomes 1 for all of them. Then it becomes 1 over k squared, which is the p series with k equal to 2. With p equal to 2, and therefore x equal to 1 also converge, but for a different reason. So as a result, the answer in the back is correct, that this thing will converge for x less than or equal to 1. And that marks the end of this section and this chapter.